So let's talk about uncertainties and inference. In fact, when you make a regression model and then predict y value, you have two kinds of uncertainties. Well, first of all, it's uncertainty which is called a fitting error. In my case, it's second. It's a fitting error. It's because we cannot predict y precisely by using x, simply because x does not explain the whole variation of y, right? So you remember in our case it's only 78%. So that's the fitting error. The x cannot explain y fully. Okay, and that's the error of prediction. Sometimes it's also called lack of fit. That's the standard deviation. So you remember that's the standard deviation for your error. So that gives you an uncertainty for the fitting. So fitting error. What else we have? Well, we also have uncertainty in regression coefficients or sampling error. Okay. So what it means? Let me show you an example. So that's the population. So we have beta 0 and beta 1. We never know them, right? So instead we take a sample. So we have B0 and B1. But we would like to use this model for the population. Okay. We don't know B0, beta 0 and beta 1. So it means that if we take a new sample, in the new sample we will have another coefficients beta 0 and beta 1. In another sample we will have another coefficients B0 and B1. So it means that for new sample your line will be probably a little bit like this, then maybe a little bit like this. So there is always an uncertainty in the position of this line. This is the true position. This position will always be different from the true one. Okay. How big the difference is? Of course, it's the uncertainty on the position is here. So we have uncertainty in the coefficients. So we need to know a distribution and calculate maybe the confidence interval for the coefficients. That's actually what we need to do. Luckily, the regression coefficients follow the distribution we already know. It's a t-distribution. So we can use t-distribution to calculate the standard error, to calculate the uncertainty, to calculate the confidence intervals for the beta. In the case of the slope of B1, the standard error of the slope depends on two things. It's a standard error for the prediction, and then and the variance for the x. Okay, and then you can use this formula to calculate the confidence interval for the beta 1 for the slope. And then you can also make a test if you want and get a p-value, how likely the slope for the population is equally 0, so you don't have any model at all. For B0 and beta 0, the standard error looks like this. So you can also see that it depends on the standard error for B1, and it depends on the variation of x. And then that's how to calculate the confidence interval for the beta 0. If you use R and use this LM function for making model, you can get it clearly by taking a summary for the model or using conf.in to calculate confidence interval. That's what I'm going to discuss in the last lecture, how to do things in R. Okay. Now, how this uncertainty in the regression coefficients influence the uncertainty in predictions. Okay. So this is how it is. Okay. Look. The red line is our model. The dashed lines show you the area where the true model is. So the true model can be like this, or can be like this, or can be like this. We don't know it. The true model means it's a model for the population. So the true position of the regression line is unknown, but we can calculate uncertainty in this position. And these dashed lines, they show you this uncertainty. You can see that the closer you to the center, the smaller uncertainty is. And then the more far you go from the center, the larger uncertainty is. You can calculate this uncertainty using this formula. Okay, so this is the uncertainty. So you can see it depends on how far you from the center. It depends on the spread of x, and it depends on your sample size. So this is the uncertainty from the regression coefficients, because we don't know the real position of the regression line. Okay, and then we also have uncertainty in fitting. We already know it's TSE and just TSE, right? So if we add 1 here, we will take both into account. So this is the uncertainty from the position of regression line, and this is the uncertainty from the fitting error. And that's now the dashed line shows you the uncertainty for the predictions of y. So it means that every time you predict that y is here, in fact y is somewhere here. Somewhere here. So that's the uncertainty for the predictions. Okay. Then you can see also a small band around the center, but it's not very big in this case. So if we look at these two formulas, you can see that sample size matters, right? The bigger sample size is, the less chance that you will have the uncertainty for the position of the regression line. For example, if sample size is very large, this will be almost zero. This will be almost zero. Imagine that a sample size, for example, is 100. This will be 0.01, right? This will be also quite small value. So in this case, if sample size is large, you can use a simplified formula like this, okay? But if your sample size is small, that's the way how to calculate the uncertainty in prediction. And therefore, if you have a y value equal, for example, to, I don't know, 6, it doesn't mean that it's 6. It's 6 plus minus this uncertainty. You can think about error margin similar to what we have in the average values. Okay. Now let me show you an example. Let's say, let's take our case. So this is our model, 830, right? Then let's say that we know that n is equal to 32. We have 32 values in our sample, and that's the degrees of freedom at 31. Okay. Let's calculate a t-value for 95% confidence. So we will calculate the uncertainty interval for 95%. For this, degrees of freedom is 2.04. You can use ICDF for t-distribution to check this. And then the average x, the average age, we have is 34.4 years. Okay, that's the standard deviation for the x. And that's the error. We already know it because we already calculated it previously, right? So that's what we know. Now let's take the following. We have a person who is 36 years old. What will be the salary of this person? Well, no problem. We can just use this formula, use 36 instead of x, and then calculate the salary. So the predicted value is this one. It's 28,735 35 euro per year. Okay, but what is the uncertainty for this prediction? Well, we know all the values, right? This is 36. This is 36, and this is 34.4. This is 9.5 squared. This is 31. This is 32. And we know these two values as well, right? So we can simply calculate it, okay? So if we take x minus mx squared, we will get 2.56. So here in the denominator, we have 2.56. Then n minus 1 times the variance of x is 2,809, okay? So you know that the ratio of these two will be a very small number, right? Then 1 over n is 32. So if you do all the calculations, that's the uncertainty you will get. That's the uncertainty you will get, okay? So it means that when you predict that it will be 28,735, in fact, it's not. It will be 28,735 plus minus the uncertainty. Plus minus the uncertainty, okay? And the uncertainty is quite large here because the model is not actually, it's not ideal in this case. In the mini project, you will be able to practice also how to calculate these uncertainties. And probably you can try to change n and see how big the difference in uncertainties will be if n is relatively large. For example, if n is between, instead of 10, you have 30, instead of 30, you have 50 or 100 and so on. And then you will see that for the small n, you indeed have uncertainty larger than you should expect. But if n is relatively large, then it will not, this part will not give you a big difference in the uncertainty.